Good day, my name is Oscar Sanchez Jimenez, and I will be presenting our paper entitled Estimation of the Extreme Probability Distribution Response of Offshore Structures Due to Current and Turbulence. The co-authors of our research are Professor Emmanuel Pañaco, Professor Eduardo Sousa, and Professor Ruben Sampaio. The focus of our study are the extreme values of the response of submerged offshore structures subject to the effect of a fluid flow that can be modeled by a stochastic field. It is so because of physical phenomena like turbulence and current. When the field of velocities is assumed to be Gaussian, the forces acting on the structure are generally non-Gaussian. The responses of the structure will be stochastic processes, and thus their extreme values are described by a random variable. The distributions associated with this random variable are called the extreme value distributions, or EVD for short. Finding this EVD for shear force and bending moment is our goal. To do this, we will use the theory of translated Gaussian processes, as well as other theoretical results coming from the transformation of stochastic processes. This is the Morrison formula. It is used to describe the hydrodynamical force that a flow exerts over a structure that is immersed on it. It has an inertial component, in our case it is negligible. The other is said to be the drag component. To say that the inertial component is negligible is equivalent of saying that our loading conditions are quasi-static. This diagram is a visual aid for the information available during the physical process. At the input, we have a stochastic field modeling the velocity field of the flow. It is characterized by a mean, a variance, and a covariance function. We have chosen to express the latter in this fashion, the product of a spatial component and a temporal component. This input acts on the mechanical system and produces an effect, the output, or the mechanical response. In our case, we study the shear force and the bending moment. We infer characteristics from the response for those of the input by means of uncertainty propagation. In this case, an integral transformation of square Gaussian processes. For instance, we can express the mean of the response in terms of the known characteristics of the input. Now we will present some theoretical results useful to achieve our goal. The first are relationships between the EVD and the mean number of upcrossings for a given stochastic process. These are the basic relationships we have. This can be simplified applying properties like ergodicity if we know them for the stochastic process under study. If we also know the PDF, the formula can be expressed like this. If we assume that the peaks of the process under study are rare and statistically independent, which is called the Poisson hypothesis, we arrive at an exponential expression of the EVD in terms of the mean number of upcrossings of said stochastic process. Here we present a synthesis of the theory underlying the translated Gaussian processes. The translation of Gaussian processes serves to generate a generally non-Gaussian process from a Gaussian stationary process with zero mean, applying the following transformation. This transformation is defined, as we can see here, by the composition of the CDF of the target translated process and the Gaussian parent process. Here, X sub g is called the Gaussian parent process, and y hat is the translated Gaussian process. To the right, we have some relationships that allows us to obtain information of the translated Gaussian process as a function of those of the Gaussian parent. Of interest are the PDF of the translated process, and the correlation or covariance functions that allows us to calculate the PSD, the power spectral density of the translated process. Another useful result is this equation that links the mean number of upcrossings of the parent Gaussian process with those of the translated process. It is valid if H is monotonic. This is an schematic representation of the proposed methodology. We begin on the left. We have the velocity field, stochastic field, that is Gaussian in our case. It is characterized by a mean function, a variance function, and a PSD. We want to get as much information about the response as possible from those available for the input. This information is, however, limited, and to get it, we use results from cuts about the quadratic forms of Gaussian random variables, and also results from uncertainty propagation over an integral transformation of monomial processes. The information we obtain consists of the marginal CDF and the PSD of the output. Now we solve the inverse problem to determine the appropriate Gaussian parent process that will better fit the information we have about the response once we apply the transformation. We are interested in the EVD, but we have no information about the response. We will determine the appropriate Gaussian parent process to generate the necessary information to find the EVD. This step is iterative. Since X sub g is virtual or fictitious in the sense that it isn't a physical quantity, we chose the PSD in such a way that upon applying the transformation, the resulting translated process fits the target PSD of the response process. Here we have the steps used to iterate over the respective PSD. Once we have done this, we can apply the transformation on the Gaussian parent process that we found, and we obtain the translated Gaussian process that coincides with the prescribed response process that we have calculated in previous steps, although generally the PSD will often be an approximation of the original one. In this diagram, we have the physical configuration of our problem. We have a cylindrical pile submerged, fixed to the seabed. It is subject to the effects of a unidirectional flow. We have the height of the pile and the distance from the seabed to the sea surface. This distance to the sea surface is important on the description of the velocity field. Here we summarize the numerical values of the parameters we have used. We have chosen realistic parameters for this kind of application retrieved from the pertinent bibliography. There are also parameters corresponding to the discretization scheme used in some of the calculations we will present later. We solve the problem under these conditions for a 5-minute interval, or a short-term study, and for a 3-hour interval, or long-term study. To complete our formulation, we have done 2 fits of experimental or measured data carried out on sea basin locations. The data of these fits come from studies relevant to the conditions of an offshore submerged structure. For instance, exploratory studies for prospective turbine sites, tidal turbine sites. To the left, this polynomial fit has been made using data of mean velocity profiles, and to the right, we have a logarithmic fit based on measured PSDs of sea or oceanic states. These are the results of applying the proposed methodology. We compare them with 2 Monte Carlo-based methods. We have generated the velocity processes on the time domain. We have calculated the mechanical response for these time signals, and we have used on them an empirical CDF algorithm and direct counting of upcrossings. We see here the comparison for the 5-minute simulation. For the lower end of the percentiles, there is some discrepancy, but there is close agreement on the higher end, and this result is particularly useful for from a design perspective. Here are the results for the 3-hour interval. The EVDs calculated by the three approaches fit much more closely, even for lower percentiles. Having compared our results with two Monte Carlo approaches and seeing they are in general good agreement, we have compared our methodology with a widely used method in offshore engineering. We have chosen the SRSS method as a comparison. It is known that one of the limitations of this method is the case of sums of processes that are strongly correlated, a situation that arises regularly in this type of problem. This correlation is expected since the random forces acting on a pile, for instance, are produced by stochastic fields that are spatially correlated. The classic SRSS under these conditions tends to undervalue the EVD. We see here how the results of the proposed methodology, which have been corroborated by direct Monte Carlo time domain simulations, differ from those of the SRSS under the conditions that are known to be limitations for it. Furthermore, it is seen that the SRSS assigns a higher probability of occurrence to load levels that are lower than those seen in Monte Carlo simulation and also the proposed methodology. To conclude, we have presented a methodology to determine the EVD of immersed offshore structures subject to random loading under quasi-static conditions as described by the Morrison formula. The methodology is analytical and uses translated Gaussian processes, integral transformation of monomial stochastic processes, and analytical results from quadratic forms of Gaussian random variables. There's evidence that this methodology does not suffer from some of the limitations that commonly used method on the field do, like the case of correlated stochastic processes. There is good agreement between the proposed methodology with direct Monte Carlo simulation, particularly on the region of the EVD that is most useful to design decisions based on the maximum occurrence approach. Continuation of these results go in two main directions. The first is the application of the proposed methodology to situations in which the inertial term of the Morrison formula is not negligible. In other words, dynamical loading conditions. The second one involves the modeling of a velocity field of an input as an stochastic field that is not Gaussian. Thanks for your attention, and I'll be glad to listen to your questions and commentaries during the corresponding session.